Okay, we're going to continue on here. We're talking about really classifying reactions, I think, and balancing equations. So obviously, when we talk about balancing equations, we want to make sure that we only change the coefficients, which are, again, the numbers that come in front. And they do all has to be whole numbers. And they also has to be the simplest set of whole numbers like we talked about. So again, if you balance an equation, you look at the coefficients and you can round all of them down or reduce them all down by a common number and still have a common number. That is what you should do. We also saw that you can use a fraction to balance an equation, but you do need to get rid of the fraction when it's all said and done and clear the fraction by multiplying by the denominator. Lastly, we also talked about the idea that if you do have some polyatomic ions within an equation that you're balancing, sometimes it's a lot easier just to keep those together and balance them as units rather than go element by element. So sometimes a lot faster and a lot easier doing that. We started talking about ways to classify reactions. And remember that pretty much there's those three reasons why a reaction takes place, which is, again, as we talked about, the formation of a solid or a precipitate is referred to. There is the formation of water. And there are electrons being transferred. So as I talked about last time, there's really two big categories of reactions. There are double displacement reactions, which is where we kind of got into last time. Double displacement reactions you can always recognize because you will always have two ionic compounds together. And always when you have two ionic compounds together, this is always the pattern that occurs. The two positive guys will once again sort of switch partners. And they will make two new ionic compounds on the product side. And the double displacement reaction also has two sort of more specific classifications that fall under that sort of big umbrella. And that was what we focused a lot on last time, which is a precipitation reaction. And a precipitation reaction is when one of these guys basically makes a solid or a precipitate. And again, that is basically what accounts for one of the three reasons why a reaction takes place. The other thing, as we will see today, is an acid-base reaction. And in an acid-base reaction, pretty much one of the things that you make is water. And that is, again, the second reason why a reaction takes place. So again, under sort of the big umbrella of double displacement reactions, there's more specific classifications like precipitation reactions or acid-base reactions, which both of those are still double displacement reactions. Again, it's just a more specific way of classifying those reactions. The other ones, as we'll mainly focus on today, is redox reactions. And redox reactions basically involve a transfer of electrons. So these type of reactions, which we'll kind of talk about more today, is really the third reason why reactions take place. And underneath sort of the big umbrella of redox reactions are more specific classifications of reactions like synthesis reaction, decomposition reaction, single replacement reaction, and so forth. Now, in the sort of talking with double displacement reactions, we came across three very common equations that we see. One is the molecular formula, and the molecular formula, our molecular equation, sorry, the molecular equation is basically you write everything out just like normal. So we got a little sodium nitrate plus some, that's not going to do it. Sodium chloride would be better. Oops. Or just erase everything and start fresh. Let's try that again. Sodium chloride plus some silver nitrate. And in this case, this is going to be, again, a double displacement reaction. And we know that because that's a positive, negative, positive, negative. So these guys, again, are going to switch partners. And remember that when you do that, you want to make sure you do get the right equations first or formulas before you even worry about any type of balancing. This will give us our AgCl and sodium nitrate. We could also use solubility rules, as we talked about, to help us decide if we are going to get a solid or not when these two ions come together. And there are some of those rules, like sodium is soluble in everything, which means because of that, it gets the aqueous symbol. Nitrates are also soluble in everything. There's no exceptions, which means it will be an aqueous guy. Silver chloride, chloride soluble in everything, but there are three exceptions: silver, lead, and mercury one. And in this case, that is one of the exceptions. So instead of, again, chloride being soluble, it would be the opposite, which means it's insoluble, and we would get a solid that's formed in this particular case. And once again, on both of these guys here, sodium and nitrate, they are both soluble in everything. There's no exceptions, which means they would be aqueous. So this equation is balanced. This would be our molecular equation. As we talked about, though, in solution, because these guys are strong electrolytes, some of them, and some things are weak electrolytes, we do have these guys basically breaking apart. So anything that is a strong electrolyte will break apart in solution, and we could write an equation that shows that. Anything that's a weak electrolyte or a solid liquid, or for the most part a gas, will stay together. So this guy will also break apart. The solid here will stay together because it's a solid. And our sodium nitrate, which is aqueous, will break apart as well. This is what is sometimes referred to as the total ionic equation. And we write this equation to show what's really happening in the solution. And when we pour all these guys together, we basically got some ions apart. Again, in the total ionic equation, ions should have charges. Also, again, we do not break up anything that is a weak electrolyte. Remember that most of your weak electrolytes are probably going to be weak acids or bases. So we have that list of like 6 strong acids and also some strong bases. So again, if it's probably not any of those, you could probably safely assume it's going to be weak. Also, again, solids, liquids, and so forth, we do not break up. When we get the total ionic equation, we should always be able to find ions on both sides of the arrow that look exactly alike and have exactly the same numbers on both sides of the arrow. These, again, are what are referred to as spectator ions. Spectator ions are much like the name implies, they're just hanging around watching. They are not important in terms of the product being made, so we typically cancel those guys out. That leaves us our real reaction that's actually taking place when we mix these two solutions. The silver from the sodium chloride will go find the chloride. I'm sorry, the silver from the silver nitrate will go find the chloride from the sodium chloride and come together to make this solid here. And this is known as the net ionic equation. It is pretty much the equation that shows you exactly what is happening here and going on in this reaction. Clearly, this is a precipitation reaction. Also falls under the big umbrella of double displacement. And again, because we made a solid here, that's really one of the reasons why this reaction took place, is that formation of that solid. Any questions on any of those things there? All right, so I think we left off with this example. So for each of these, let's write the total ionic equation as well, and the net ionic equation. And actually, I think I will change this to let's do this guy, and let's do WKBr. All right, let's do that one there. See what you come up with. So obviously molecular equation as well. Okay, so let's take a look. So first off on this one here, you should be able to recognize as a double displacement reaction as we have two ionic compounds. So remember that when we do have to predict what's on the other side of the arrow, we want to just make sure we get the equations down first, and then we should worry about the balancing. So again, they're going to switch partners, which basically means we're going to take a potassium, which is the basic unit of KBr and Br minus. And for the other guy, that is lead with a +2 and nitrate with a -1. So those are the basic ions of those guys on the left-hand side. We're just going to switch partners. So when we put these guys together, that's going to be the K plus and NO3 minus, which will give us the proper formula in this case of KNO3. And now we're going to put these guys together here, and that's a +2 and a -1, which means we should end up with PbBr2. Any questions on the formulas there? Now that we have that, we can do the balancing. We could also do our solubility type of rules. That's potassium and nitrate together, which definitely is going to be soluble. That is bromide, which is soluble in everything except for lead, mercury, and silver, which in this case, that would then make that a solid in this case. So this would be a precipitation reaction as we made a solid based on the solubility rules. Now we can balance it. Again, I do have a nitrate on the left and right-hand side, which means I can keep that together. I have two nitrates on the left, one on the right, so I can balance it by putting a 2 in front of the nitrate on the right. That also gives me two potassiums, which is where I should go next. And that gives me two bromines, which is exactly what I need on the right-hand side. So I am now balanced again, keeping that polyatomic ion together. Much easier and quicker to balance this equation than going sort of element by element. Question on that there. Now that we have this, we can break this guy apart into our total ionic equation. This obviously would be our molecular equation. So our total ionic equation, we're going to break apart the KBr because it's a strong electrolyte. So two bromines and two potassiums. We will get one lead with a +2 charge. The 2 for the nitrate will come to the front and give us two nitrate ions, which is basically what the 2 means. On the other side, we will have two potassium ions and also two nitrate ions. And obviously here our solid will stay together. Question on the total ionic equation, or complete ionic equation. Again, as we talked about, this is where we're going to find our spectator ions. So it looks like potassium on each side, and also looks like nitrate there on each side is exactly the same on each side. Those are going to be our spectator ions. Remember, we pretty much just cross those guys out as they're just watching, not really making any type of product. So really in this reaction, it is in the net ionic equation, it is the lead with a +2 charge coming together with the bromide with a -1 charge to make this solid a PbBr2 solid. Any questions on any of that there? All right, then looking at our next one here, again, you should be able to recognize this also as a double displacement. That's an ionic compound. That is an ionic compound. Once again, pretty much the only reaction where you lay up two ionic compounds to start with. So that's always going to switch partners. So again, we're going to switch partners here. We want to write the formulas correctly when we do so. So sodium here is +1, by the way. And sulfide is -2, calcium is +2, and chloride is -1. So when these come together, we get NaCl. We do not get Na2Cl2. No such thing. Yes. So we get NaCl, basic units together. Don't worry about the balancing. And when we put our calcium and sulfide together, that's just one of each of those. We now can use our, if we wanted to, our solubility rules here to see what's going on. That's going to be aqueous because it has sodium. And sulfide is normally insoluble, but actually calcium is one of the exceptions if you look at solubility rules. And so instead of being insoluble, this will be soluble. We can balance it for good measure, put a 2 there, I suppose. That means that in this reaction, there actually is no reaction. The reason there's no reaction is if we take it to the next step, which is the total ionic equation, it would break apart when we look at it into 2 sodium ions and a sulfide ion. This guy would also break apart into a calcium ion and 2 chloride ions. On the other side of the arrow, we will have 2 sodium ions and 2 chloride ions. And we will have a calcium ion. And I'll go underneath as I ran a little bit of room there. We would also have a sulfide ion. So when we look at what is our spectator ions in this case, I got 2 sodiums on the left and right. I got a sulfide left and right. Got a calcium left and right. And I got a chlorides left and right. They are all spectator ions. They're all going to cancel out, which means we really have no reaction happening. All we have going on is everybody's just floating around together, but nobody's coming together. They're just all floating around in the solution part as ions. So basically no reaction in this case. We would not see any type of solid formed. And because we didn't make a solid, we didn't make water, and there was no electrons transferred here, there's no reaction basically that occurred in this case. Any questions on that there? Yeah. Yeah. Would it be wrong if you are you talking about put a 2 here or yeah, it would be because it wouldn't be balanced, right? So all three of these equations when you write them, you want to make sure that they're all balanced. And if you balance the molecular equation correctly, when you go through the other 2 equations, you should remain balanced all the way through. That's also what I mentioned, I think, last time as well. You will know if you kind of screwed up the balancing part of it or did something incorrect when you get to the spectator ions. And if you look on the left and right hand side, you don't have the exact same numbers of those ions. It's the same numbers on each side. So for example, if I got here and I had 2 potassiums on the left, but only 1 on the right, something's not right with whatever you did, either balancing or how you broke apart that guy. So they should always remain balanced pretty much all the way through all those equations. And they should remain that way as long as you start with that molecular equation being balanced. Other questions? So we can have obviously a no reaction, even though we throw some ions together. Again, it's just basically means they're all just floating around. All right, for this one, why don't we just do the balanced equation? We don't have to do all 3, so just the balanced molecular equation here with the states. Okay, so let's take a look at this one. So again, you should hopefully recognize as a double displacement reaction. I got 2 ionic compounds. Again, we're just gonna switch partners here. So again, just the basic units of these guys in terms of ions, which would be ammonium, and the other guy would be sulfate. That is lead with a +2 charge, and that is acetate. That has a -1 charge. So again, when we switch partners, we want to get our proper formulas down first. That should give us a little ammonium acetate. And the lead and the sulfate will come together, and we would just need 1 of each of those. At this point, we can use our solubility rules. Ammonium is soluble in everything, so are acetate, by the way. So we're good to go on that. Sulfate there is going to be insoluble here with lead. So that will make our solid in this particular case. What's left to do here is a little bit of balancing. So truthfully, you got two polyatomic ions on both sides. You got ammonium on each side, and you have acetate on each side. And frankly, you have two on the left of each of those and one on the right. So you could very quickly fix that by simply just putting a 2 there, and that will balance it up real quick and be done. Any questions on that one there? All right. So obviously you need to be able to write those three equations, identify spectator ions, predict products in these double displacement reactions. Any questions on any of that? Okay, so we've been focusing in here on pretty much precipitation reactions, which again, this can be more specifically classified as a precipitation reaction because obviously we made a solid. The next sort of type of double displacement reaction we're going to talk about is acid-base reactions. And when we have an acid-base reaction, we pretty much get usually two things that occur. An acid, as we've, I think, touched upon, is anything that has the ability to really produce free H plus ions in solution. So it has the ability to, when it goes for a swim, release H pluses, which are referred to as protons. And sometimes also in acid-base chemistry, the hydronium ion and H plus are basically the same thing. So they're used interchangeable for an acid. And a base, on the other hand, is something that has the ability to basically produce free hydroxide ions, basically floating around. So that's basically what a base is, and that's basically what an acid does. And whenever you take those two things together, especially a strong acid with a strong base, for sure, you will get two things. You will get a salt plus water. Again, here it is the formation of water, which is why this is taking place. If you remember that again, it's like the second reason why a reaction takes place is you made water, and that's essentially what you're doing in these type of reactions. Where does the water really come from? It usually comes from the H plus from the acid, the OH minus from the base. Those two guys come together basically to make your water. What is a salt? A salt is just an ionic compound. And I would say in most cases in a reaction of an acid and base, the salt is going to be an ionic compound that's, really the spectator ions when you think about it. They're just kind of floating around. They're not going to be doing anything. What is really happening in pretty much all these reactions with acid and bases is basically the formation of water. That is why they are sometimes referred to as acid-base neutralization reactions because you're neutralizing, you're making water basically is the idea here. I made the list, I think, the other day, but this is sort of a partial list here of our strong acids. I think added to that again is HBr and HI are your strong acids. Here are some moderate acids, which would be considered weak pretty much below those. So most of these guys are going to be weak acids. And again, if you had any type of strong acid, it will be a strong electrolyte and 100% break apart. If you have a weak acid, it would be considered a weak electrolyte. And when you get to, say, your total ionic equation, you would keep it together. So there is a difference whether it's a sort of a strong acid or a weak acid. As I mentioned yesterday, I think if you just remember these six, and it's not one of those six, it's pretty good chance it's going to be weak. And you probably will get the answer correct in that case. Most strong bases, by the way, have hydroxide in them. So as we can see here, most strong bases will have hydroxide. And for the most part, if you kind of roll, like I might have mentioned, lithium, sodium, potassium, and go right there to calcium, strontium, barium. For the most part, these are considered any of these guys with OH minus pretty much your strong bases. So right there in group one, coming into group two, that again is why they are referred to as the alkali metals and alkaline earth metals. The word alkaline means basic. So that's where a lot of strong bases basically come from on the periodic table. Once again, if it's not one of those, it's probably going to be more on the weaker side in terms of a base. So as I mentioned before, acid-base neutralization reaction, if we take something like our hydrochloric acid and react it with sodium hydroxide, this is a strong acid and base. This is also still a double displacement reaction because this is basically H plus and Cl minus. This is Na plus and OH minus. So this is still, even though it can be more specifically called an acid-base neutralization reaction, this is still a double displacement reaction. So the same thing is going to happen. These two guys are going to swap partners, basically. And that will give us our water from the H plus and OH minus from the base and the acid, and our Na plus and Cl will come together and make our salt here and water in this particular case. So once again, our water is coming from basically the H from the acid, the OH from the base is essentially where our water is basically being generated from. Now, because this is a double displacement reaction, we can break this apart like any other one and write, besides our molecular equation here, our total ionic equation. And that's going to be, in this case, H plus Cl minus plus Na plus, which is obviously a strong base, will break apart. When we get to water, that's a pure liquid. Remember, solids, liquids, pretty much gases, and weak electrolytes will stay together. So our water here will actually stay together. And we will get Na plus and Cl minus. We can also look like normal in our total ionic equation for our spectator ions. I got a chloride there. I got a chloride there. Got a sodium there and a sodium there. Those are our spectator ions like normal. And just like normal, we will cancel those guys out. And that will leave us our net ionic equation, which is the H plus from the acid is basically you can go find the OH minus from the base. And lo and behold, they're going to make water, which is the real reason why this reaction is taking place here, the formation of water. You can take any combination of strong acid, strong base, and that is always your net ionic equation at the end. That's pretty much where you will always hit, is basically the formation of water. Unlike a precipitation reaction where you could actually see the precipitate, usually when you do this, you can't necessarily see the water being made. It just looks the same kind of, but you are making water, and that is, again, the reason why this is taking place. So any combination, like I said, you can take nitric acid and potassium hydroxide. You can take any combination you want, and if you boil it down to the net ionic equation, it's always going to basically be the H plus from the acid coming together with the OH minus from the base to make water. Any questions on that there? Again, why it's referred to as a neutralization reaction, because you basically made water in this case. Yeah. Now, before we look at that there, let's take a look actually at this here. What happens though if I had this combination? Let's just say I had, we'll do HF plus potassium hydroxide. All right, why don't you do this? Why don't you give it a go, see what you come up with, write the balanced molecular equation, write the total ionic equation, and the net ionic equation. Okay, so let's take a look and see this. Obviously, this is an acid, which is hydrofluoric acid. That is a base. That is a strong base. By the way, if you're not sure about the acid, we could run through our list of strong acids, which looks something like this. And clearly, I do not see this guy on my list of 6 strong acids. That's going to tell me that this is going to be a weak acid in that case. Still going to do a double displacement reaction. So again, we're still going to have the H from the acid go hook up with the OH from the base. So that is still going to make my water. And then obviously my salt here in this case will come from those two guys coming together. That's K plus and F minus, which will give me KF in this case, would be aqueous because potassium is soluble in everything. So this would be my molecular equation. It actually is balanced in this case. Now, when I go to my total ionic equation, the HF, should I break it apart? I should not, because it's a weak acid, which means it's a weak electrolyte, which means weak electrolytes mainly stay together. So we should keep it still together. The potassium hydroxide, which is a strong base, is a strong electrolyte, so that will break apart. So we will get K plus and OH minus. Should I break apart water? I should not, otherwise it wouldn't be water. So a pure liquid there, we would keep together. And potassium fluoride is a strong electrolyte, so it will break apart into potassium ions and fluoride ions. So this would be the correct total ionic equation in this case. Here we do have a weak electrolyte, a weak acid, so we do need to keep it together. Because we have to keep that weak electrolyte together, that's going to affect how many spectator ions I actually have. In this case, I only actually have just one spectator ion. It is the potassium on each side that looks exactly the same. So that's my spectator ion. We still do the same thing. We will cancel it out, and that will leave us our net ionic equation, which is HF plus some hydroxide. We'll make some water, and this guy right here, which is this conjugate base, actually. And so we'll get a little different sort of total ionic equation and net ionic equation. When you have a weak electrolyte involved, you'll actually have less spectator ions. And obviously your final equation there will look a little bit different than normal as well. Question on that there. So that's how you would handle if you had a weak electrolyte, which again, in most cases, is probably going to be a weak acid or weak base. You want to keep it together when you go through the total ionic equation. And again, that will probably limit your spectator ions. And you could just do the same steps after that, obviously. Any questions on that there? Yeah. So another sort of ending, if you will, for a double displacement reaction, in addition to making water or making a solid, is it can also form gases sometimes. So gases is a product that can be formed as a result of that sort of double exchange. Wherever I went with that, there it is. And there are really kind of, in a double displacement reaction, two sort of ways that a gas can be generated. One way that a gas can be generated is actually just a direct result of a product being made. So one of the products that's being made is a gas, and that's what we see here. This is potassium sulfide, positive, negative, sulfuric acid, positive, negative. They're going to switch partners, the potassium and the sulfate, the hydrogen and the sulfide going to come together, and that will directly make hydrogen sulfide gas, which nobody wants to smell. Does not smell pleasant. And it will just be made as a direct, basically, result of those guys exchanging. The second way that a gas is kind of generated through a double displacement reaction is actually, it is kind of a twofer reaction that occurs. The first reaction that occurs is actually the double displacement reaction. So here, if we started with potassium sulfite and sulfuric acid, we will get our double switch here. And we will make potassium sulfate and sulfurous acid. Now, what happens at that point is pretty rapidly, this sulfurous acid will actually go through another type of reaction, which is known as a decomposition reaction, which basically means it's just going to break apart. And that's what we see here. This guy will kind of relatively quickly break apart and will then produce SO2 gas. Another common one is if you take like an acid and some sodium carbonate, for example. Also a double displacement reaction. Minus. These guys are going to come together. These guys are going to come together. That's going to make a sodium chloride plus an H2CO3, which is carbonic acid in this case. Maybe a little 2 there and a 2 there to balance everything out. But that carbonic acid will very quickly also go through a decomposition reaction and make CO2 plus water. So it'll make that CO2 gas through a decomposition reaction. Like Alka-Seltzer, plop, plop, fizz, fizz. Yeah, so the fizzing and stuff that you put in there, that's the idea that's happening there. Yeah, so we're going to look at a table here that will kind of help you make that decision. So let's take a look at that table so you have an idea as to, whether you'll kind of get the gas directly or will something go through it. Most of the time, this is going to be kind of your table that'll kind of help you decide, are you going to get that or not? If you have a metal that's with sulfide or a metal that's with HS minus and you react it with an acid, that's going to be probably your route to directly make hydrogen sulfide gas. So basically, if you got anything that's with sulfide and anything with HS in it or HS minus, and you react it with an acid, is the important part. You got to react it with an acid. That's going to generate just directly that gas. The other sort of routes here to CO2, SO2, and ammonia are sort of indirect routes. They're going to be kind of decomposition reactions that occur. And that's going to be anything with carbonate or bicarbonate and react it with an acid. You're going to make that carbonic acid, which will break apart, and that's going to get you your CO2 gas basically in water. Anything basically with sulfite and hydrogen sulfite, again, reacted with an acid is an important part of that, will produce you what we saw in that previous example, that sulfurous acid, and that guy's going to basically break down into basically your SO2 gas. And lastly, ammonium, like ammonium hydroxide, and you react it with a base, will produce ammonia. So that is the other. So those are the three sort of common routes to those gases. And for us, those would be the only ones that you would be, sort of responsible to know off of this table. So again, carbonates leads you to CO2, sulfites basically leads you to SO2 gas, and ammonium will lead you to NH3 or ammonia. Again, you need to react the carbonate and the sulfite guys with acids. The ammonium needs to be reacted with a base, basically, and that will get you your guys there. Any questions on that there? All right, so that is basically our double displacement reactions, which once again, as I mentioned, takes care of the two of the three reasons why a reaction takes place: formation of water, which we see with acid-base reactions, precipitate being formed that we see with precipitation reactions. Now we're pretty much going to talk about the rest of the type of reactions, and these are going to be our redox reactions. And redox reactions, as I mentioned before, basically stands for oxidation and reduction reactions. Now, the good news about oxidation reduction reactions is it always occurs together, which means if somebody is being oxidized, there should be somebody that is being reduced. The nice thing about that, as you might see, is all you have to do is be able to figure out one of those things, who's being oxidized or who's being reduced. And by default, the opposite thing is happening to the other guy that's there. So that's kind of a nice thing about that. You just got to pick out one of them. There are a few definitions for each of these, but we will focus in on just the two that we commonly use here in general chemistry, which is the oxidation means that somebody has lost electrons or will lose electrons. Reduction again means that somebody has gained electrons. If you go off to organic chemistry, you'll see the other two definitions of these things, which is oxidation could mean that you gain oxygen as you go from reactants to products, or you lose hydrogen, H2, as you go from reactants to products. Reduction is the opposite definition. In that case, you will lose oxygen as you go from reactants to products, or gain hydrogen. We oftentimes look at hydrogen and oxygen when you're doing organic chemistry because it's all about nonmetals mostly, and we can see oxygen and hydrogen a lot easier than looking for oxidation states, which is typically what we look at here in general chemistry. Once again, people sometimes remember this as Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Other people, again, are fond of the oil rig. Oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig and you don't have to choose which one you want. He'll go grr and you'll be good on either one that you do that. So how do you really know if something is being oxidized or something is being reduced? The way that you really know is you look at what is known as the oxidation state, or sometimes referred to as the oxidation number of a substance on the left-hand side of the arrow to the right-hand side of the arrow and see what happens. Now, sometimes people confuse oxidation states and numbers with charges. And sometimes the charge on elements are the same as the oxidation state, and sometimes they are not. And that sometimes confuses people. So, for example, something like chlorine. We normally think of chlorine when it has a charge as having what type of charge? A -1, right? But if you have chlorine in something that maybe we drew, like, maybe something like this. Yeah, pop up guy there. Maybe something like that. I don't know. That's 18, 25, 26, like that. Yeah. Looks right-ish. All right. In this case, the oxidation state of chlorine is actually +5. Yeah. And it is not -1 like you assume it is in chloride. And that is because the oxygens here are carrying a -2 oxidation state. So if you add up all those -2s, that's -6 +5 leaves you a -1 left over. So the oxidation state is different than the charge we think of in elements when they're in an ionic compound. In an ionic compound, the sodium and the chloride come together. The chloride is going to just grab those electrons and fully take them, right? They're going to transfer. And that would be the oxidation state in sodium chloride of chloride. But the chlorine in here is different because it is now sharing electrons, and electrons have not been transferred. And basically, in this case, the more electronegative guy is the oxygen. And the definition of electronegativity is electrons go towards which thing? The more or less electronegative atom? The more. So in this case, because he's sharing electrons with all these oxygens, all the electrons are moving towards the oxygens, which makes this chlorine more and more positive in this situation because it's actually sharing those electrons unequally, not losing any, but they're just moving away from him and making it more and more positive. So sometimes it's hard for people to wrap their head around, like, because we're beat into our heads the sort of ionic charge of all these elements, right? When they make charges. And that is true if it's an ionic compound. Again, if you were asked what the, for example, oxidation state of NaCl, the Cl is in that case, it is -1 because, again, that's an ionic compound. Electrons are completely transferred. But when they start sharing electrons in covalent bonding, things that we normally associate, for example, with negative charges, can have a positive oxidation state. So oxidation state in numbers, not necessarily exactly what, the charge is, but it is sort of the charge that they take on based on who they're sharing electrons with. That's also why, if we put ClO4 minus, which is like 24, and 7 is like 31, plus 1 is like 32 electrons, and we draw that, it will look something like this. In this case, each of these oxygens will still have a -2 oxidation state. That's now 4 oxygens, right? At -2 each, that's -8. Overall charge is -1. The chlorine here gets even more positive. It actually has a +7 oxidation state because it has the extra oxygen sucking electrons away from it and making it more and more positive. So it depends on what those elements are attached to as to what their oxidation state may be. And again, when you're looking at something that is sharing electrons, the oxidation state may not be the same charge that you associate with that element when it's in an ionic compound. Any questions on that? Oxygen is always a really good place to start, and it is, I would say, 99 times out of 100 going to be -2. There is one exception, which is if the oxygen is not really oxygen, but it's actually peroxide, one of those polyatomic ions. In the case of peroxide, it's actually -1. And that's the only time oxygen would be -1. Probably, like I said, 99 times out of 100, if you see an oxygen, it's probably safe to assume it has a -2 oxidation state. That would be the one exception where it would be -1 in that case. And that's because here hydrogen would be +1. When you add up all the oxidation numbers, they should equal the overall charge on that molecule. And since hydrogen peroxide is 0, it should add up to 0 when it's all said and done. Other questions on that? So how do you know really when you're looking at it, if you could sort of figure out the oxidation state of everybody? Is somebody being oxidized or is somebody being reduced? There's a really simple way to do it, which is like a good old-fashioned number line. And I believe to the right of 0 are positive numbers, to the left of 0 are negative numbers. So when you lose electrons, which is what happens when you go through oxidation, do you become more negative or more positive if you lose electrons? It is positive, right? So you lose electrons, you have more protons, right? So if you look at the oxidation state or number of somebody on the left-hand side of the arrow to the right-hand side of the arrow, and you chart that on your number line and you're moving in this direction, the more positive direction, that guy is going through oxidation. Same thing if you are gaining electrons, which is what happens when you go through reduction. If you gain electrons, you're going to become more negative, right? Because you have more negatively charged electrons that you're gaining. So if you follow on the number line, the oxidation state from the left to the right-hand side, and you're moving to the left towards the negative numbers, that thing is going through reduction. And that is like a super simple way to just figure out is it being oxidized or not. So for example, if we looked at, what happens when we make something like sodium chloride, sodium metal by itself plus some chlorine gas makes some sodium chloride, right? And we'll do a little balancing since this is chemistry, I suppose. There we go. Now, when we look at what's happening with each of these sort of elements on each side of the reaction here, if I have an element that's by itself, not combined with anything else, does it have a charge? The answer is no, it does not. Things, again, only get charges when like a metal and a non-metal come together, right? So this is sodium metal, which has no charge or really a 0 oxidation state is what it really has. Chlorine, that is naturally how chlorine comes, right? By itself, uncombined, which means it will also have a 0 oxidation state. Yeah. Now, when those two guys get together, the sodium and the chloride, we now have an ionic compound, right? And in this ionic compound, they will have their normal charges. This is when they get charges, right? When they come together. The sodium here will be +1, right? And the chloride here would be -1. So again, this is a case where chloride, because it's an ionic compound, the Cl is -1 is the oxidation state in this case, because really electrons are being transferred. Basically, that's what's happening here. So how can I determine who's being oxidized and who's being reduced? Very simply, I'm going to start with the sodium. The sodium started at 0 and ended on the right-hand side at what number? +1, right? So it's moving in this direction. Is it being oxidized or reduced? Try that again. So it started at 0 and it ended at +1, which means it's moving in this direction. It's becoming more positive. Did it get oxidized or reduced? Got oxidized, yeah. So that is as simple as you could do it, yeah. That thing just went through oxidation. Let's look at the chlorine. The chlorine started at 0 as well, right? It ended at -1, which is moving in this direction, right? More negative, which means the chlorine here is going through reduction. By the way, once you figured out that sodium is going through oxidation, by default, the other guy has to go through reduction. They always happen together, so they never happen separate. One thing doesn't happen, the both will always happen. That makes sense because we know what really happens in this case, right, is our metal will transfer its electrons, which is the third reason why a reaction takes place right there. Yeah, this type of deal, a redox reaction. Electrons being transferred is why this is occurring. By the way, when you have a metal and a non-metal coming together like we just did here, which one should always be oxidized? Between a metal and a non-metal, which one always loses electrons and becomes positively charged? The metal, right? The metal is always the one that becomes a cation. So super simple if you have an ionic compound happening. If you have a metal and a non-metal coming together, it should always be the metal being oxidized. The non-metal is always the one that gains electrons, right? That's how it becomes negatively charged. It should always be the one that's going through reduction. So that's a really easy way to remember that. Works great if you're doing metal and non-metals together, but we don't always do metals and non-metals together. Let's just say on one side of the arrow, I had iron 3 chloride. And on the other side of the arrow, I had iron 2 chloride. Is the iron being oxidized or reduced in this case? So let's take a look. So obviously I said the name. So the iron on the left-hand side has what type of stat charge? It is a +3, right? Because that's -1. There's 3 of them. Here again, the oxidation state is going to be the charge because it's an ionic compound. So it'll be our normal sort of oxidation state. On this side, the iron is going to be +2. Yeah. So again, if you're not sure, just go to your number line. +3 would be like here, right? And +2 heads me in which direction? To the left, right? Because that would be like 3, 2, 1, 0, right? -1, -2, -3. That means it is being oxidized or reduced, the iron here. It is being reduced, yeah. What's happening with the chloride? Anything? Nothing's happening. It's staying the same, right? It's -1 on both sides. As you might imagine, that is our friend, the spectator ion. If we had a real reaction going on here, it's just hanging out, going for a swim. It's really nothing's happening with him at that point. Any questions on how to identify that there? Yeah. All right, so let's get officially into this, I suppose. All right, so if we look at oxidation and reduction reactions, as I mentioned before, that is really the reason why that takes place, which is the transfer of electrons. We could take a reaction and actually split it up into what is referred to as its half reactions. And if we take a reaction, for example, like the formation here, magnesium oxide, and we take our 2 magnesiums plus our oxygen goes to 2MgO in this case. So when we look at this, we can identify once again that it is the magnesium going through oxidation, because over here, this is magnesium by itself, which means it has no oxidation state, 0. Oxygen is naturally how it comes uncombined, which means it also has a 0 oxidation state. When those two hook up together, that is when the magnesium gets a +2 and the oxygen gets a -2, right? So again, if you follow the number line here for magnesium, it started at 0, ended at +2, which means it's going in the positive direction. That means magnesium is being oxidized, which is why it's the oxidation half reaction happening. If you look at the oxygen here, it starts at 0 and ends at -2, which means it's becoming more negative. And the oxygen here is going through reduction, which is why that is the reduction half reaction. So we could write these half reactions to show both the oxidation part of the reaction and the reduction part of the reaction. So this is the oxidation part half reaction going from 0 to +2. Because it is losing electrons in the reaction, electrons should be a product in an oxidation like they're being given off. So we put the electrons on the product side like they're being given off. Why is it 4 electrons in this case? Each magnesium is going to lose how many electrons? 2. And how many magnesiums do we have? 2 times 2 is 4. So that is why we have 4 electrons. 2 from each magnesium is going to be lost in this particular case. Now, the oxygen here will then pick up those 4 electrons, and we see it on the reactant side of the equation, the electrons. And that indicates that it is a reduction half reaction, like it is gaining those electrons. So those oxygen is going to pick up those electrons. By the way, it picks up the same 4 electrons that were lost from the magnesium. It's like a balanced situation. However many electrons the metal loses, for example, or the person being oxidized loses, is the exact amount of electrons that whoever's being reduced will gain in this case. That's because we have 2 oxygens, right? And each oxygen will end up at a -2 charge, which means each oxygen gained 2 electrons, and 2 of them will give you the 4 electrons it needs from the magnesium there to be gained. These are called half reactions because, frankly, when you add them back together, anything on opposite sides of the arrow can cancel out either completely or can reduce down. So you can think of the arrow almost like an equal sign, like you're subtracting it to the other side, basically. So there's 4 electrons in the bottom one and 4 in the top one. And before you add these equations back together, the oxidation half reaction, the reduction half reaction, the one thing you should always make sure of is they have the same number of electrons in both half reactions. If they do not, you might need to multiply a half reaction by a number, or you might need to multiply both half reactions by a number to get each of them to have the same number of electrons. The idea here is what I said earlier. The amount of electrons lost should be the amount of electrons gained. So when you add these half reactions together, before you do that, you got to make sure they both have the same number of electrons. If they don't, you need to multiply it. Then everything on the left-hand side stays on the left-hand side, and everything on the right-hand side stays on the right-hand side. Since these are 2 ions, they're going to come together to make my ionic compound in this case. And again, that is basically why they're referred to as half reactions, because when you put them back together, you get the whole reaction. Yeah, you get the whole thing, the oxidation and reduction thing occurring. Any questions on that there? So this also happens, by the way, with metals and metals and single replacement type reactions. So for example, here we have a piece of zinc sitting in there, and that's a solid piece of zinc which has no charge, 0 oxidation state in this solid form. You put that in a solution of, say, copper 2 nitrate. You have some copper 2 ions floating around. You also have some nitrate ions probably, but they're not important in our conversation. They're just spectator ions floating around basically in the solution. What's going to happen in this case is we only find ions in the solution part. Yeah. So what the zinc's going to do is it's going to lose its electrons and get oxidized. When it does, zinc will then become a positively 2 charged ion and now go for a swim. The copper that's swimming around in there will pick up a couple of electrons from the zinc because it will lose 2, right? It makes a +2 charge. So it will lose 2 electrons. And when it does so, the copper is going to go, I'm done swimming. I'm going to come out of the pool and I'm going to come over here as solid copper. And that's why you can see the bottom here, which blue is not the best color there, I suppose. The bottom of that piece of zinc is now discolored, right? And that is all the copper jumping out of the solution and now becoming solid, and all the zinc jumping into the solution and becoming ions. You'll also notice perhaps the color of the solution when it started. Copper is blue, right? Remember the flame test a while back, right? It was blue. So that solution that's blue on the left has a lot of copper 2 ions floating around, which is why it's blue. But as they continue to jump out of the solution, when they gain those electrons and become reduced, the solution now gets more colorless, right? And that's because the solution now has a bunch of zinc ions floating around, and zinc ions are colorless. So this is actually visually an oxidation reduction reaction. Here, the copper is being reduced because it's gaining those electrons. The zinc is being oxidized because it's losing those electrons. And again, that transfer of electrons is why this redox reaction is occurring, why this reaction is actually occurring, and you would actually see that. Any questions on that there? So ions, if you're not sure, always in the solution part, floating around basically is where they are found. And that's basically what we see here. This is the reaction that accounts for what we just saw here. This is really a single replacement reaction. And that is still a redox reaction. So what is happening here? If we look at the oxidation state of zinc, it is 0, right, by itself in its standard state. That is copper 2 sulfate, which means the copper has a +2, and I'll keep those two guys together. The sulfate has a -2. On the right-hand side, the zinc now has a charge, right, because that's zinc sulfate. That's an ionic compound. The zinc has a +2 charge. The sulfate here still has a -2 charge. And the copper is all by itself. No charge or oxidation state. So if we do our little number line here, we can figure out again who's being oxidized and reduced. When I look at the zinc, it's starting at 0. And on the right-hand side, the zinc ends at +2, which means it's going to the right. Going to the right means more positive. Oxidation or reduction, that guy. Oxidation. We could look at the copper. The copper is starting at +2, which is about here in the number line. And on the right-hand side, the copper ends at 0, which means it's moving in this direction towards 0, becoming more negative. The copper here is being reduced. Again, I could have known that by just simply knowing that the zinc is being oxidized because they always occur together. What about the sulfate? Anything happen with the sulfate? There's nothing happening with the sulfate. We could actually demonstrate this with our 3 types of equations that we've done before with double displacement. This is the molecular equation, right? We could also write a total ionic equation for this reaction. The zinc here has no charge, so it obviously stays together. The copper 2 sulfate is a strong electrolyte, so it will break apart into copper 2 ions plus our sulfate. The zinc sulfate will break apart into zinc with a +2 charge and our sulfate. And our copper there will stay the same. When I look at this, what are my spectator ions? Sulfate. Is there any other spectator ions? There is not. And a common mistake that people make is I got zinc there and zinc there, and they cross them out. They are different, right? The zinc on the left has no charge. It's not an ion. It's just an element. On the right-hand side, that has a charge. So they are not ions, just both of them, and they cannot be spectator ions. They're not the same. Same thing with the copper. They do not have charges on both sides. That means that the only spectator ion that we have in this case is actually the sulfate. And we could write our net ionic equation, which basically describes what's happening here, our zinc plus our copper 2 is going to make our zinc with a +2 charge and our copper with no charge. Basically, what's happening here is the zinc is offloading 2 electrons over to the copper 2 guy that was floating around in that solution. So you could write a total ionic equation, net ionic equation for a redox reaction as well, and it works the same way. Once again, you could also see very commonly you will only have one spectator ion as well when you do that. Question on that. All right, so finish up with this last one here. Copper wire reacts with silver nitrate to form silver metal. What is the oxidizing agent and reducing agent in this case? So let's talk a little bit about those two terms here to finish up on. Reducing agent and oxidizing agent. Reducing agent and oxidizing agent are different than the question of what is being oxidized and what is being reduced. So the reducing agent is the substance that is being oxidized, while the oxidizing agent is the substance that is being reduced. So when you're asked about what is being oxidized and reduced, that is a different question than what is the oxidizing agent or reducing agent. The reducing agent is the substance that is being oxidized. So what does that mean? That means that the person going through oxidation, if they're going through oxidation, they will lose electrons. And when they lose electrons, that's going to force somebody else to gain electrons, right? And be reduced. So it's going to cause the reduction in somebody else, which is why it's known as the reducing agent. The oxidizing agent is the one that will be reduced. So if it's being reduced, it needs to gain electrons. The only way it can gain electrons is to cause somebody to lose electrons. And when it causes somebody to lose electrons, that thing is going to be oxidized. So it's causing the oxidation of somebody else. That would mean in the above example, the zinc is going through oxidation. The zinc here would be my reducing agent. It is going to cause the copper here to gain electrons when it loses its electrons. The copper 2 really is going to be my oxidizing agent, because in order for the copper 2 to gain those electrons, it's got to cause the zinc to be oxidized and lose the electrons. So the easiest way to remember the agents is it's opposite of the name. So if you're looking for the reducing agent, you need the one that gets oxidized. And if you're looking for the oxidizing agent, you need the one that gets reduced. Again, those are different questions. If you're asked that, what's the reducing agent, oxidizing agent, or what is being oxidized and what is being reduced. So again, here, zinc is being oxidized and is the reducing agent. Copper 2 here is being reduced, and it is the oxidizing agent. Question on that there. So in the case of magnesium and oxygen, which one should be the oxidizing agent? Oxidizing agent should be, in this case, the oxygen is being reduced. So that's the oxidizing agent. This would be the reducing agent. The reducing agent, the oxidizing agent, the thing being oxidized and the thing being reduced should always be found on the reactant side of the equation. Yeah, so all those things are found on the reactant side of the equation. Any questions on any of that intro to redox? Sounds like fun. All right, we're laid up there.